Hi friends, so today we are going to start Math Question Bank 5, and in this question bank I'm going to discuss 10 questions and then I'm going to solve them. Now these questions are all pertaining to a certain theme, that is the solution of nonlinear equations, and most of you know this is a favorite question in many examinations, in many interviews, in many tests and so on. And if you are a teacher you can use some of these questions in your tests or in the different questions you ask students. And also, if you are a STEM manager or you may be somebody who is interviewing PhD students, then you can use these questions also. So I'm going to explain some of the methods out there which are quite popular, such as the bisection method, the Newton-Raphson method, the secant method, and so on. And I'm going to also introduce you to some very interesting functions, specifically the Lambert-W function, which can be used to solve many different problems which are there, and the type of questions which are often asked in different math competitions and math Olympiads. So let's begin. So the question number one asks you to solve this following equation graphically. And this is the equation we are going to continuously come back to in today's lecture. That is 3 to the power x equals x to the power 9, and you have to solve for x. Now what this problem tells you to do is that it has given you a small interval where actually the root lies, or rather I should say one of the root lies, and it's telling you to solve this equation. So this is one of the simplest ways to solve an equation, provided you know where its roots lie. And this is a question which can often be asked to students, and they can plot this particular functions and try to get the root. So in this case, for example, if I were to plot these functions separately, so let me try to plot 3 to the power x and x to the power 9. So if you see 3 to the power x, it's the blue line here. If you see x to the power 9, it's the orange line here. And you can clearly see that these two are meeting at a certain point, which is approximately at x star equals 1.15. So that's the x-axis. The x-axis here is x, and the y-axis represents the value of these functions. Now, one of the things about these functions is that they grow very rapidly. So they start out with some small value at x is 1, but they will start growing very rapidly after, for example, 1.25. Now, this is one of the roots, and this root is important because we are going to try to find this root using various numerical methods, and also we are trying to get an exact solution for this root. So this is something which you now know about this problem. Now you could also plot the function f of x. So we could say, instead of writing 3x equal to x to the power 9, I could write a function f of x as 3x minus x to the power 9, and I could plot this function, which we have done here. And here you can clearly see that if we plot this function, this goes through the point 0 at again somewhere close to 1.15. So that's one of the zeros, or the root of this function f of x. Now this is again a very standard way to find the root of a function, and whatever be the function, if it has a root, you can find it using this method. Now of course what can happen is that you may have to plot the function over various values out there as far as the number plane is concerned to get the root. So now let's start at some numerical methods. So numerical methods are extremely useful for solving equations, and one of the things numerical methods can help you do is that they can often solve equations which are intractable in terms of closed form solutions, or which you cannot solve using classical mathematical methods. So let's start with a simple method first, which is known as the bisection method. And the question here asks you to solve the problem 3x equals x9 using bisection method. And this particular interval is given, x is between 1 and 2. So first I'm going to try to explain the bisection method to you and how I have solved it here. So in the bisection method, what we do is that we form a function in this form. So we have formed the function fx is 3x minus x to the power 9, and we obviously know that we want to find a zero of the function. So if we were to plot a function, the function would go through the point fx is 0 somewhere, and that's the point we want to get. So let's think about this function here. Now what's going to happen is that on the left side of this particular root, the function value is going to be positive, and on the right side the function value is going to be negative. So this always happens when you are at a root. So what this tells you is that if you are able to bracket the root, which means that you're able to find 2 points, one point at which fx is positive and one point at which fx is negative, then the root is likely to be between these 2 points. So this is known as bracketing the zero or bracketing the root. So that's what we are trying to do here. So let's start with these points which were given 1 and 2. So x was 1 and x and 2, and we calculate the value of fx using this function here. So at x equal to 1, fx equals 2, and at x is equal to 2, fx is minus 503. So clearly you can see the function looks something like this. And so what is obviously going to happen is that the root lies between 1 and 2. Of course, we have seen the root is somewhere near 1.15 in our previous graphical exploration. So now what we do is we bisect this particular interval here. So between 1 and 2, we get the midpoint as 1.5, and we calculate the function value at this midpoint. Now this function value here is a negative number. Therefore, I know that the root is between 1 and 1.5, because at 1 it is positive, at 1.5 it is negative. So now I find the midpoint between 1 and 1.5. So I bisect this new interval, and what you are seeing that at each iteration I make, this interval is shrinking. So I get 1.25, that's the midpoint between 1 and 1.5, and at this point the function value is minus 3.5 and so on. So again here we have a negative value, we have a positive value at 1, so we know the roots lies between 1 and 1.25, and so I find the midpoint of 1 and 1.25, that is 1.125, and I calculate the function value here. Now this is the first time the function value actually becomes positive here, which means that we have crossed the root here. So what now happens is that we can bracket the minimum, or rather the root again, and that's going to be between this point 1.125 and the last negative point, which was 1.25, and so that's 1.1875, and that gives me a negative value now. So now I know the root is between 1.125 and 1.875. So I keep doing this process continuously, and as you can see, the interval keeps shrinking, and after some time, as I keep bisecting this particular interval out there, I end up with a point which is very close to the actual solution, where I'm getting something like 1.150877, and before that I got 1.151365. Now after a certain point, what you do is that you can take the mean of the 2 points here. So these points look pretty much converged, and the mean comes to 1.15063. Now of course you see the bisection method is very nice. It's something which you can program very simply, and it's going to converge to the root of the problem. Now one of the things of course you can see is that its convergence is very slow, so that's one of the problems of the bisection method. But do remember that some of these numerical methods I'm describing to you, these can also be used to write computer programs. They can also be done on Excel spreadsheets, and you can use these different methods to test people's competence in any programming language. So if you are trying to test a particular candidate on a language such as Python or maybe MATLAB or Julia or anything else, you can ask them to write a simple program to solve any of these problems using a particular method here. So again, I have done this calculation in Excel, so it's very easy to do it in Excel. Now let's look at a faster method of solving this problem, which takes use of derivative information which we did not use in the bisection method. So question number 3 asks you to derive the Newton-Raphson formula to solve a general function fx equal to 0. So this is a very well known and popular method, the Newton-Raphson method, and we are going to derive it. So let's try to do that here. Now to find out the Newton-Raphson formula, the most important step is that we can express this function f of x as a Taylor series, and that's what we have done here. And what we have done is we have retained only one term. So essentially the Taylor series is going to be valid very close by to the point where you have taken the Taylor series. So here we have taken the Taylor series of the function f of x about the point x0. So we get fx is fx0 plus x minus x0 f dash x0, where f dash of course represents the derivative of f with respect to x. Now x0 is the particular point here about which we are taking this Taylor series, and what we do is that we set this function to be equal to 0. Now this particular equation is only valid in the vicinity of x0, so we are going to move in the vicinity of this x0 point, and we are going to try to use this method to converge to the actual root. So now from this equation I can immediately write this equation here, and I can simplify it to the form x equals to x0 minus f x0 by f dash x0. Now I can think about solving the equation fx equal to 0 by repeatedly using this formula here. So what we do is we write this formula as x1 is x0 minus fx0 by f dash x0, and then I generalize it to any iteration k. So the formula becomes xk plus 1 equals xk minus fxk by f dash xk. Now of course to start off this method you require a value of x0. X0 is the initial guess, and a good initial guess is certainly going to help you a lot in convergence of the Newton-Raphson method. A bad initial guess is going to sometime cause situations where the method simply will not converge. Now the first value x1 I simply get by using this formula. The next value x2 I will get using this, and so on. So in the next value x2, x1 actually becomes the previous value you use. So actually you just need one starting guess. After that the method takes off on its own. So now before I try to use this method on this particular equation which we are dealing with, that is y equals 3x minus x to the power 9, let's try to first differentiate this function, because we are going to need the derivative of this function to use the Newton-Raphson method. So that's question number 4. Find dy by dx given that y equals 3 to the power x minus x to the power 9. That's our function here. So to differentiate this function, we can use the fact that whenever we are differentiating a function like this, we can split the problem into differentiating each of these two functions separately. So that's what I've done here. And of course, x to the power 9 is very easy to differentiate. That's simply going to become 9x8. But this one is slightly more complex. So let's look at how to differentiate 3 to the power x. So let's call this y1 is 3 to the power x. So if I take log on both sides, I get log of y1 is x log 3. And then I differentiate this function. I get 1 by y1. dy1 is log 3 into dx. And so from this I can write dy1 by dx equals y1 log 3, and y1 was 3 to the power x, so I get dy1 by dx is 3 to the power x log 3. Of course here this is the natural logarithm which we write as ln. Now I have this derivative, so I can write dy by dx is 3 to the power x log 3 minus 9x to the power 8. So this is the derivative of the function we started with here, and now we are ready to use the Newton-Raphson method on this particular problem. So that brings us to question number 5, which is solve the equation 3x equals x to the power 9 using Newton-Raphson method with an initial guess of x is 1.5, which means that x0 is going to be 1.5. Now this is something very important in Newton-Raphson method and numerical methods, is that you often need a starting solution to start the algorithm. So here I have written the function f of x out. The thing we have to do is we have to use Newton-Raphson method with x0 is 1.5. So I can immediately write fx0 in this form. I can write f dash x0 because I just calculated the derivative in the previous question, and so I get x1 is x0 minus fx0 by f dash x0. Now this is something which is very easy to program. I have written a simple program in Microsoft Excel, and so you can see here x is there, fx is there, f dash x is there, and then the new value x1 is there. So for example, when I want to start this process off, I start with x0 is 1.5. I calculate fx at this 1.5. I get this number here. I get f dash x is this number here, and then I use this formula here to get x1 is this value. Now this x1 becomes my starting point for the iteration 2. So I start with this point, and then I calculate fx and f dash x at this point, and I get a new point which is 1.24. And you see now here quickly the algorithm converges, and x1 actually becomes 1.15084, which is very close to the final answer by iteration number 5, and certainly we can say by iteration number 6 the algorithm has converged. And you can also see the value of fx is decreasing, and by iteration number 8 it has become even lower than 10 to the power minus 8. So certainly the Newton-Raphson method converges very fast compared to, for example, the bisection method, because here you are using derivative information, and whenever you use derivative information your methods tend to converge much faster. Now I'm going to introduce a new method known as the secant method, and the secant method uses a particular approximation of the derivative. So to motivate that approximation of the derivative, I'm going to pose another question here to explain a certain concept, and this question is find the derivative from first principles of fx is x cube. So this is a very simple problem. You of course know the answer is 3x square, but the question asks you to calculate this from first principles. So if you want to calculate the derivative from first principles, you have to come to the definition of the derivative itself, which is that f dash x equals limit h tends to 0 f x plus h minus f x by h, where h is a small perturbation or a small deviation from the value of x. So this particular definition is the mathematical definition of the derivative, and of course this derivation, or rather this definition, holds as h tends to 0. So let's try to apply this to the function x cube. So what I do is I substitute fx equals x cube in this equation here. So I get x plus h cube minus x cube by h. Now here the problem will basically be easy to solve if I expand x plus h cube out, which I have done here. So to do that I take x plus h, I multiply it by x plus h square. So I get this here. So x plus h square is going to give me x square plus 2xh plus h square. I further expand it out, I get this value here. So one thing is going to give me x cube plus 2x square h plus xh square. So that's this quadratic multiplied by x, and then I take this quadratic and I multiply by h throughout, so I get this particular function. Now I can simplify this function. If I were to put this function in f dash x here, I get this value here because there is a cancellation in terms of x cube, so the x cube terms get cancelled. And also I can simplify some of these terms because there is a term 2x square h, there is another term hx square, so I get 3x square h. There is a term xh square, there is another term 2xh square, so I get here 3xh square, and there is a term h cube, so I get that here. Now I divide this equation throughout by h, so I get this here, and now I can invoke the limit that h tends to 0, in which case this term and this term are going to vanish, and I'm only going to be left with f dash x is 3x square. So this is a question again which is often asked by people, and so you now know how to do it. Now one of the important things which we are going to use now is this particular definition of the derivative, but what we are going to do is that instead of taking the limit, we are going to assume that this derivative is approximately equal to this particular expression here. This is sometimes known as the forward difference formula, and very often in numerical methods you can calculate the derivative of a function x by using a formula like this where h is a small number. So let's come to question 7 now, and this question involves deriving the secant formula to solve this function. This is also sometimes known as the secant method. So what we are going to do is we are going to now start with the Newton-Raphson method, which I had derived a few slides before. That was xk plus 1 is xk minus fxk by f dash xk. And I'm going to simply change k to k plus 1. So I get this method here. This is nothing but the Newton-Raphson method. Now, what this lets me do is that it lets me calculate f dash x of k plus 1 using the forward difference formula which I just discussed in a previous question. So instead of using h here, I use the difference between xk plus 1 and xk. So I can write the derivative in this form. So it is the perturbation in the function value as the point xk changes to xk plus 1 divided by xk plus 1 minus xk. And so I take this particular approximation of the derivative. Remember, this is an approximation, so I'm not using the equal to sign because that will only happen in the limit as these two become virtually identical. So once I take this f dash x k plus 1 and put it in the Newton-Raphson formula, I get this formula here, and this is known as the formula for the secant method, sometimes known as the secant formula. Now, this not only plays an important role in numerical methods but also in optimization. So there are many methods in optimization which are also based on the secant formula. So what we are going to do now is we are going to use this formula, and to use it we are going to require two initial guesses. So we are going to require x0 and this should be x1. So there is going to be x1 here. So there are two initial guesses out here which we are going to require. So now the next question, number 8, is solve 3x equal to x19 using the secant method, and two starting values are given that x is 1 and 1.5. So that's what we are going to use. We have the function here. We are going to use secant method. We are going to use x0 is 1 and x1 is 1.5, and so I can get the point x2 using the secant formula in this form. So here you can clearly see that the derivative here has been expressed as a finite difference derivative. Now what I can do here, I can take x0, x1 as given, I can calculate fx0, fx1, and then I can immediately get x2 from this formula. Now I take this x2 and I again redo this particular problem. So now 1.5 is made x1 and I use this x2 value as x1, and I do this again, I get this new root here, and I continue doing this particular process, and so at the end of it I converge here. So this one takes slightly more time to converge than the Newton-Raphson method. So here I have converged here at 1.15082. That's the solution at iteration number 10, and by the next one the function value has basically become 0. So of course we can see the Newton-Raphson method is the fastest method here because it's using the exact derivative information. Sometimes that is hard to calculate. The advantage of the secant method is you don't need to calculate the derivative exactly. So you are relying on function values which are simpler to obtain in most cases. And of course the bisection method was simply using a very simple philosophy of bisection. Now sometime you always have a bisection method as a backup, because what happens with these methods which are involving derivative is that sometimes they may fail, because what may happen, the derivative may go to 0, in which case the Newton-Raphson method may have problem. Similarly, if these two numbers become very similar, you could have a problem in the secant method, but the bisection method is going to be relatively robust. So sometimes bisection methods and methods like that are used as safeguard techniques in numerical analysis and numerical computation. So that brings me to question number 9, which is that is it possible to actually solve this equation? And this is not an easy equation to solve, but I'm going to solve it in the next slide. And you're going to discover some new methods. Some of you may know it, but some of you may find the method to be rather interesting. So what we of course do with a problem like this is that we generally invoke log immediately. So we take log on both sides and we get this here. X log 3 is 9 log x. And I can write this as log by x is log 3 by 9. And I can write this then as log x e to the power log x is log 3 by 9, and then I can express it like this. So what I have done here is I have put a negative sign. I have put minus ln x into e to the power minus log x here. Now why did I do this? Now I did this because there is something known as the Lambert-W function, and the Lambert-W function, what it does is that when it is applied to something like a to the power ea, it gives me a. So this is a specific property of the Lambert-W function. This is a very important function, and this function I can then apply to this equation on both sides here. So just like we can take log on both sides of an equation, we can take the Lambert-W function on both sides of the equation. Now sometimes this Lambert-W function is known as a power log function. So you can think of it as a modern or new definition of the log function, which you may not have known before, though this function has been around for a long time. Now once I use this, I can immediately see that the left hand side is going to become minus log x, because this is nothing but a as far as the Lambert-W function is concerned. And then I get this equation here, which is negative log of x is the Lambert-W function minus log 3 by n, and so I get log n is minus w of this value. So log 3 by 9 can be done, or rather calculated in a calculator, and you will get this value. So x is e to the power minus w of this value. So remember, w is the Lambert-W function. Now the question is, how are you going to calculate this? Now you can go to many tools which are there on the internet itself. For example, you can go to Wolfram Alpha. This is a free tool. If you go to this website, what you are going to do is you are going to type Lambert-W and the value here, so which I have put here, and so it's going to give you a particular value. So in this case, you see I get 0.140479. So of course there is a negative sign here, so here it becomes 0.14. Here it was minus 0.14. That was the Lambert-W function for this value here. So I get x star is equal to 1.150824 by taking e to the power of this value, which you can calculate in a calculator. So in many such problems, the Lambert-W function is going to help you solve the particular problem. So now returning to this whole issue, let us come to question number 10, and question number 10 says that explore this problem graphically around x is equal to 1 and x is equal to 27. Now those of you who have been looking at my previous math question bank lectures would know that there is another root at x is 27, and I'm going to show that to you again. And the question says, what are the roots? So let us try to explore this function here. So I will explore 3x to the power x9 graphically. So again, I have plotted this function here, and you can clearly see that there is a root at x star is equal to 27. So that's a root right here. And so the function fx goes in a manner like this here. That's one of the roots. Now, of course, the second root we already know. We found this using the Lambert-W function and using bisection method, the Newton-Raphson method, the secant method, and so on. And that root was at 1.5, 1.15082.